Good afternoon, everyone. My name is Tanvir Ahmed. I am a graduate student from the Department of Mechanical and Aeronautical Engineering of Clarkson University. Welcome to my talk on fluid mechanics and droplet transport from production of unvoiced fricatives. COVID-19 pandemic has highlighted the importance of airborne droplet transport as an efficient vector for virus transmission. Predicting the risk of virus transmission during the speech depends on knowing the droplet size distribution and the velocity field that is produced at the exit of the mouth. The primary motivation of this work is elucidate the droplet size distribution and velocity field production at the exit of the mouth during speech. Recent work has identified that human speech produces droplet size distribution that are similar to coughing and singing. Although the total particle expiration are higher for coughing than speaking. Although one cough can produce as many as 5,000 particles, phonation has been shown to generate up to 40 particles per second, indicating that 2 to 10 minutes of phonation can produce as many total particles as one cough. Prior work has found that time average velocity at the exit of the mouth to be range of 1 to 4 meters per second for a variety of phrases. Time average measuring during running speech, however, obscured the highly transitory nature of voice production. From preliminary flow visualization during consonant production, we have found that fricatives that from the very narrow occlusion at the mouth, such as F and TH, are most likely to produce high velocity bursts of air. This observation leads to the objective of this work. First, determine the droplet count and size distribution for consonant production, and second, investigate the fluid mechanics at the exit of the mouth for these same consonants, where initial emphasis is placed on the investigating the phone F and TH. Droplet measurements were performed using a TSI 3321 aerodynamic particle sizer in a laminar flow hood, resulting in a 0 particle count in the background. A sound pressure level meter and a microphone simultaneously recorded the sound production. We have investigated 16 different consonants by saying a consonant, a intonation. For voiced fricatives, voiceless fricatives, voiced plosives, voiceless plosives, and nasal consonants. 5 utterances were repeated over a 10-second sampling time. This was then repeated 3 times for each utterances. Data were collected from 2 males and 1 female. During the recording, participants maintained a sound pressure level of 80 dB, measured 15 centimeters from the exit of the mouth. We collected the raw data to consider particle size during sampling and transport through the tubing, connecting to the APS, which was found to be less than 5% for particle less than 10 micron in diameter. Humidity measuring in tube, mouth, and ambient surroundings revealed negligible droplet size reduction due to the evaporation. So we reported the size of the aerosol as they were measured in the APS. The cumulative number of particle product produced by all participants for each utterances varied significantly, from 33 to 88 particles. On average, nasal consonant produced the most particles. However, a large sample size is needed to ensure a statistical significance. Interestingly, droplet production per utterances also varied significantly from person to person, as did average droplet count. The average particle count averaged across all utterances, as shown in the box plot, was 22, 20, and 8 for the 3 participants. Particle size distribution across all utterances, which is not shown here, revealed consonant production produces particle sizes between 0.7 to 6 microns, with a mean size of 1.9 and a median of 1.53 micron. The standard deviation was 1.53. Next, we perform fluid flow measurements to provide qualitative and quantitative analysis of the expiration velocities. Initial flow visualization in a freezer at negative 10 degrees Fahrenheit investigated visualization of the consonant production, indicating fricative consonants produced by occlusion at the mouth, resulting in the highest exit velocity. Hence, subsequent investigation focused on these utterances. The trajectory angle of exploration is an important parameter to determine the settling time of droplet. To investigate the trajectory of consonant exploration, power flow visualization was performed using a laser light sheet to illuminate the expelled cloud. Snapshot in time allowed estimation of the initial trajectory of the exploration. The approach was repeated for a variety of fricative consonants, which are plotted as a function of angle. The trajectory vary over a broad range from approximately plus 35 for alpha to negative 30 degree for alpha. To enable quantitative comparison, we designed a two-dimensional idealized human mouth model for F and TH consonants based on estimated MRI measurements of the mouth. The gap between the teeth and tongue was specified as 0.78 millimeter, which is consistent with the physiological measurements. The mouth model was placed in the shown experimental facility. Compressed air provides the flow, which then passes through a flow meter, an olive oil atomizer, and a plumb chamber before entering the mouth model. An inclined manometer monitors the lung pressure, and velocity fields are acquired with 2D particle image velocimetry with spatial resolution of 0.22 millimeter. 1000 PIV images were captured for each utterances and are presented here as a velocity magnitude contour plots for fricative F and TH at a subglottal pressure of 600 Pascal, which corresponds to comfortable phonation. Most noticeable is that the maximum velocity magnitude at the exit of the mouth is 18 meters per second for F and 25 meters per second for TH, which is significantly higher than previously measured values for running speed. The flow trajectories are angled up, which is similar to the floor flow visualization. The tongue and upper palate geometry directs the flow exiting through the tooth to attach to the upper lip. Once attached to the upper lip, the flow remains attached due to the Quanda effect and follow the curve of the lip. As the velocity of the flow decreases, the wall normal pressure gradient arising from the centrifugal acceleration of the flow decreases, and the adverse pressure gradient becomes sufficient for the flow to separate from the lip surface. Plotting the RMS of the 1000 velocity field acquisition identifies that for F, a significant speed is observed in downstream jet. This occurs due to the instability in the jet. Interestingly, the instability in the jet trajectory is not as pronounced for TH. The trajectory of the jet in the PIV measurement is significantly higher than for the flow visualization data. This is likely due to the simplification in the mouth geometry and investigating steady 2D flow as opposed to pulsatile 3D flow. Subsequent work is focused on incorporating these improvements into the model measurements. In conclusion, we found that the droplet size production by consonant production exhibits significant variability on both an utterance set and speaker basis, with nasal production produces the most droplets. However, additional data are needed to reach statistical conclusion. Expiration trajectory were found to be vary widely over a range of 65 degrees, which has significant implications for predicting the large droplet transport that follows a ballistic-like trajectories. The velocity magnitude for fricative consonant production was also found to be almost an order of magnitude higher than the time average velocity measurements, again indicating the importance of transient behaviors in such speech production and their influence on droplet transport. Updating the geometry and behavior of the physical model should provide more physiologically realistic data that can be used to compute momentum fluxes or predicting particle transport mechanics. Finally, I want to thank National Science Foundation and Clarkson Ignite for their funding support. Thank you, everyone.